This is our talk today, standardized stereoacuity testing in VR, vivid vision stereoacuity test. And I also have a disclosure, which is that I work for Vivid Vision and we're developing a virtual reality-based stereoacuity test. No surprise. Little bio, I went to UC Berkeley, where I got a PhD in vision science on stereoscopic depth perception. So I'm going to be telling you about something that I've been studying for 30 years now. And I love stereo vision, and was very excited to help build the new stereoacuity test. And then I did a postdoc also in stereo depth perception at Stanford. And here's a preview of today's talk. What do stereoacuity tests measure? We'll talk a little bit about stereoacuity tests in general. What are some of the causes of poor stereoacuity? Our vivid vision stereoacuity test. Now why did I put test in quotes? That's because we're taking a general philosophical approach, not of testing patients and having them do a test, but we're really calibrating their vision. And of course, as a provider and a vision therapist, your goal is to work with the patient, empower the patient, and not all patients like taking tests and being tested and asked to perform on something where they're seeing you in the first place because they're not good at it. So from our point of view, of course, it is a test, but we often call it just stereoacuity or stereoacuity calibration, especially because the results are used to calibrate your vision therapy session. Then this is, we'll talk about a little bit about how it works, and I'll show you some of the sample data that it produces. And we're going to talk about something called the composite stereo depth score. Now, I am honored today to have my colleague and co-author and even former student, Dr. Christy Law, who wrote the paper about this method with me. And we did develop this together as part of her dissertation project. She was a clinical faculty member at SUNY when I was in the biological vision department, and we formed this collaboration and developed this. This is wonderful. We think it's wonderful, and we hope you do too. And then we'll open it for some discussion. So the first thing is stereoacuity tests. They measure fine stereo. There are lots of kinds of stereo vision. Another one is coarse stereo, and then there's stereo that you can measure through changes of Vergence eye position. There's another way of people measure stereo. But stereoacuity, of course, measures fine stereo, the ability to see very small changes in depth from small binocular disparities, smaller than 600 arc seconds, for objects that are close together within the visual field, not widely separated. You can't do stereoacuity on two objects that are far apart in the visual field. You just don't have the neural wiring to make that comparison. It's usually fast, but this is what makes the response time during a stereoacuity test interesting, is because people with poor stereo will take longer to see the same amount of depth. So classically, it's fast. And then during treatment, if you're trying to treat someone who doesn't have stereo vision, what you measure with stereoacuity is usually one of the last things to recover. The other types of stereo will recover earlier, and sometimes they'll never be gone in the first place, and they give you something to work on as you try to build up fine stereo. So stereoacuity measures fine stereo. So what has to go right in order to see in stereo? Obviously, the eyes have to be looking in the same direction, so no strabismus. Neither eye can be completely suppressed. You have good optical images in both eyes as a requirement. No occlusion from cataract, no anisometropia. Anisometropia, such as unilateral hyperopias, And those things normally have to happen within the first 2 years of life for stereo to develop normally. But the result of all of these things having to go right to see fine stereo is that stereoacuity is a good tool for characterizing overall combined visual performance. And often you'll get a patient into the clinic, you'll give them a stereoacuity test, and that's how you know something is wrong. You don't know what it is yet, but it might be that they're not able to converge on the target. It might be that they have amblyopia. It might be both. It might be any number of things. They never developed the sensory ability to combine the eye's images to measure disparities, right? It could be their pure sensory function, measurement of disparities by the visual system. So it's a good overall measure. And it also then, if you can find the weak link in the patient's vision and you treat it, then you should see an improvement in stereoacuity. It affects about 10% of the population is stereo deficient. Either they're stereo blind or they're unable to see small disparities as depth. And then we've got some of the people with stereo deficiency. It's because of strabismus, amblyopia, convergence insufficiency, optical deficits, causing form depth. And then there's occasionally a developmental anomaly such as albinism, where the neural wiring in the brain is different, in addition to perhaps the retina being constructed a little differently. And you wouldn't necessarily expect a neural deficit to be treatable, but you can certainly measure and monitor stereoacuity, especially using a redesigned test like the new Vivid Vision test. During treatment, of course, one can target specific subsystems like the control of Virgin's eye posture, regulation of interocular suppression or extracting binocular disparities despite residual binocular alignment. And here we're doing the utilization of disparity to estimate depth. Oops. That. All right, now I'm going to move on now and talk about how we designed this test. The test starts at 900 arc seconds. Why not? One of the problems with a clinical test is you've got the glasses on. There's going to be often a little bit of crosstalk, or you look at the display with one eye and you can tell which what the correct answer is. Well, virtual reality, you have two displays, one for each eye separately. There's no accidental crosstalk between the images, no ghost image coming through to this eye that was intended for this eye. So you can really start wherever you want. There's no reason why you couldn't start large. And so we bumped that up a little bit to 900 arc seconds. There are a few people who will see at 900 who couldn't see at 800 or 600, which are the usual clinical starting points. And that just allows the doctor to catch a few more cases. Now, if you get it wrong at 900, we don't stay there. We'll go up to 1800. If you get that wrong, we'll go up to 3600. So that's a full degree of visual angle of disparity. And a nice rule of thumb is that 1 degree of visual angle is the width of your pinky finger at arm's length. If you turn your pinky to the sideways and you look at it, most people at arm's length, it's about 1 degree. So this is the displacement of the near object in one eye versus the other, is a full degree. And if you can't see binocular disparities in a display with 1 degree of stereo, then you really have very poor stereo indeed. You do not have fine stereo for sure, and you're even missing some of your coarse stereo. And so a lot of these folks, as we'll see, there's a way to actually still measure their vision in a very useful way by looking at the percent of trials that they see. Then if you get it correct at 900, the disparity drops down, and it goes all the way down to 20 arc seconds or even below. And I put an exclamation mark, like, that's like 20 arc seconds. Well, yeah, okay, so what? Clinical tests go down to 20 arc seconds, but here's why that's amazing. In a headset, a VR headset, the pixels are spaced at 13 of them per degree of visual angle. So those pixels are 5 arc minutes apart. 5 arc minutes times 60 is 300 arc seconds. So the pixels, one little pixel in the display to the next, that's 300 arc seconds. And yet the display is able to go down to 20 arc seconds, right? 1/30th of a pixel. And you're like, how can that be? Well, it can. It's kind of amazing. But the visual system is that good. What happens is that the visual systems can see the average location of a blob if the display uses what's called anti-aliasing. And all modern VR headsets use anti-aliasing, and it's a good thing. And that means that when you're looking at a display, it's not that each pixel is on or off. At the boundary of an object, there's a fuzzy boundary where pixels are turned on part of the way. And so if I want to show an object that's like a round object, I don't have to follow the square outlines of the pixels. By changing the pixel intensity so that this one's mostly black, and then this one's mostly light, and then this one's 50-50, I end up seeing an anti-aliased image. And this is what anti-aliasing is. It's removing the visibility of the individual pixels by using their averages and using the intensities within those pixels. And then it gets even better if the display is moving across those pixels. And we do that as well. And then the visual system can really pick out, can really see down to 20 arc seconds the location of a blob, even though those pixels are 300 arc seconds apart. So yay vision, right? This is called a hyperacuity, and some of you probably remember that term from first year in optometry school or perception class or something, but this is a hyperacuity, is the ability to see these very small differences in position. And that was an empirical result. We didn't know that would be true before we tried it. So this is groundbreaking, cutting edge clinical science here. And then the stereo depth goes up and down in this staircase until either you have 12 staircase reversals. That means you went down until you got it wrong, and then up until you got it right. Down till you got it wrong, up till you got it right. And you reversed 12 times. And if that happens, we calculate a stereoacuity in arc seconds. It's actually the average of the last 10 reversals is how you estimate stereoacuity psychophysically. And I'll show you what those numbers look like. Or until you have 20 trials at the maximum value, that 3,600 arc seconds. And in that case, we calculate the percent seen at that disparity and convert that. And then both of these numbers get converted to the CSD score, the composite stereo depth score. So I'll explain how that works in a little bit. Here's an example of the scene that you would see during the test. We use 4 targets. That's very convenient. This is left eye view, right eye view. We use 4 targets on a mesh background. And the nice thing about 4 targets is that you don't guess the correct one by accident very often. We've got 2 modes, a 5-second mode and an infinite time mode. And the standardized test, we've decided, is a 5-second test. You get 5 seconds to look at those depths. And after that, you're supposed to guess. And some patients, they need more than 5 seconds. And in that case, you can still give them the standard test to quantify their stereo position. But maybe this is somebody you want to let them practice their stereo ability, try to see it, they maybe need 10 seconds to really see it. Then you can turn off the 5-second limit. But just know that you won't be using the standardized test that can be compared over time as easily or compared with other patients. And that is the value of the 5-second standardization. It's the comparison with other patients and within a patient over time, always giving them the same test. Now you'll notice something else here. The targets are not vertically aligned with one another. It looks like there's a displacement up or down or left or right. This one kind of looks rotated, but that's just by chance. Each spot is moved randomly a bit to the left or the right. And why is that? Why do we move the spots randomly left and right? All 4 of them get moved random amounts left and right on any given trial. The reason we do that is, and if we had a live audience, I would ask for a hand, but I'll just tell you. The reason we do that is so you can't close one eye and get the right answer, right? If we had 3 of them all at the same depth, the depth of the background screen there, and one of them was displaced in one eye this way and the other eye that way, then you could just close one eye and say, oh, which one was the one that was moved? And we don't want you to do the test with one eye. And so this is a very effective method to require you to use 2 eyes. Another trick, this is virtual reality. So those spots are sitting there in depth, and one of them is closer. So you'd think, oh, it's going to get bigger. Well, we very carefully decrease the size of the object as it gets closer to your eye so that it maintains the same visual angle of subtense. You can't choose the correct answer based on its size either. Can't use its size, you can't use its position. Then you'll notice another feature of this test is the screen itself. That's a very handy reference background, and it's useful for 2 things. One reason it's useful is just that you can now compare each spot to its local background, and people have much better stereoacuity for things that are adjacent to each other in the visual field. So even that separation between spots is going to, the fact that you don't have something to compare the spot to that's right behind it is going to reduce the stereoacuity measurement. So we give you that grid. And then the other real benefit of the grid is it overcomes one of the problems in headsets once you get down to these very fine stereo. Now, this doesn't affect somebody with stereoacuity in the 60 arc second range, but once you get down to 20 arc seconds, there are very small distortions in the optics of the headset that you normally can't see. They don't normally affect treatment. You never see them during video games. You don't see them during vision treatment. But if you're trying to measure stereoacuity, which is the most exquisite visual capability we have by some measures, then your visual system can detect these small optical distortions. And it can cause the wrong target to look closer. And by providing this background grid, your visual system does this neat trick of saying, I think that grid is flat, and it measures the disparities relative to the grid. And then you can measure stereoacuity very nicely. So all of these things were built into the test from the beginning. I should say there's one other interesting feature of the test is the entire display gets larger and smaller. So when you get the answer correct, the display shrinks, the spots get smaller, the spacing gets smaller. As you get it incorrect, the spots get larger and the spacing gets larger. And that's because that's for a vision science reason, that when you're measuring large disparities, your visual system is actually using large receptive fields, and so you want large objects. And when you're measuring very small disparities, your visual system is using very small receptive fields on the neuron. Neurons, using neurons with small receptive fields, and so we want to have small objects for small disparities, large objects for large disparities. That's also really easy to do in virtual reality with a computer display. All right, let's look at some data. This chart, I've taken out the names of the subjects, and this chart shows data from 11 people. These all happen to be employees of Vivid Vision, and each person ran the test 10 times, and that's why you'll see that there's 10 staircase functions in here. And take a look at any one of these colors. Let's pick out, say, the orange color here, and you'll see that it's going up and down and up and down and up and down as the patient gets it correct for a while, and then incorrect, it goes up. They get it correct, it goes back down. The x-axis here is showing time, and the y-axis is showing what the disparity was in arc seconds. So this is a person who does not have good stereo. They started at 900, as you can see, but most of the time they went up rather than down. They got it wrong at first rather than correct. And so it went up, oftentimes it went all the way up to 3600. And now at 3600, this person can see stereo, right? So this is a person who would have been classified as no stereo with a traditional test at, it would just been greater than 600 or greater than 800. But we can actually measure it with our test. And then you'll also see the staircases are kind of doing the same thing as one another, 10 replications. And you can see that the test itself takes about 100 seconds, so it's a little less than 2 minutes to do the complete test. And we think it's worth it. We think it's worth it. First of all, it's automated, so you put the headset on the patient and let them do their own thing. You don't have to be actively testing them during it, just talk to them before and after. But the quality of the data is so good that you really nail it. And I'll be talking a little bit about how much better the quality of the data is at the end of the talk. What you can see is that everybody here you can instantly see that some people have very good stereo acuity and some people do not. Here's someone with very good stereo acuity. This happened to be Brian. I'll tell you who some of these are. And you can see here he was checking out, okay, is this really going to work if I get it wrong, right? So he went up to 3600 and got it wrong on purpose for a while just to check that the test was working properly. And so this is in arc seconds. This is on a linear scale. And so the other thing you can see is that the step sizes are smaller at small disparities and larger at large disparities. That's because they're constant on a logarithmic scale. And so that's what we will look at next. I should say, some of the tests, like here's somebody, I think this was me, and most of the time I was 100 seconds, but something interrupted me. And I had to put the test down for a while, and so it stayed the same for many seconds, and then the staircase resumed. Here's exactly the same data, but now plotted on a log scale. And so this is now the logarithm of the arc seconds. It's technically a natural logarithm being used here. And but the key thing that you can see is that the same patient who had poor stereo before has poor stereo still. And here's people with very good stereo or at the bottoms of the graphs, and then people with intermediate stereo or sort of in the middle there. And you can see the staircases are going up and down across each other, right? They're all covering the same territory, going up and down as the person gets it correct and incorrect. You may also notice that the downward slopes are gentler than the upward slopes. That when you go down more slowly than when you get it wrong and go up. There's an interesting reason why we make the downward steps smaller than the upward steps. And that's because it's a method to keep the total number of correct answers higher. When you use it's called a 3 down, 1 up staircase, the patient's going to get about 80% of the answers correct. And you still have to warn your patient, and this is very, very important. You have to warn them that this test is going to get hard until they can't do it. There's no such thing as getting them all right on this test. That's what the computer's job is. It's to go make it harder and harder until it finds your limit and then keep you there. And if you don't explain that to a patient and they think of it as a test, they're going to feel like they're getting a lot of them wrong. Well, use your words. Warn them that this is how the test works, to just ease their anxiety about that. But then also know that because of the testing algorithm, this 3 down, 1 up staircase, they're actually going to be getting about 80% correct, 82% correct. If we used 1 up, 1 down, it would be 50% correct. And that's just not as much fun. It's fun to get them correct. It's satisfying. Actually, I should tell you what it's like qualitatively, because when you get down to your stereoacuity limit, you have these illusions, right? You think that the right side is the closest, and then you look at it for another second, and now it looks like the left side is closest. So then you look away a little bit, and you look back, and sometimes you get a firm percept, and sometimes you just don't really know. And that's what happens at threshold, is your visual system is dealing with trying to extract a signal in noise, and that's really what we're measuring. But it has these interesting perceptual effects that you can explain to your patient that that's what they're going to see. Is it's going to sometimes look like it's one or the other, and it's not the display, it's their visual system changing over time. That happens, of course, in a clinical test as well. You're probably familiar with that just from looking at your own stereoacuity limit in the Rand-Dot test or a Wort circle test or something. Okay, so anyways, that's all about these logarithmic graphs. Each of those 11 people took the test 10 times, and so we can make a box plot of their results. And what were the 10 values? Now, in a box plot, this red line in the middle shows the median. So that would be the average of the 5th and 6th ones. And then we have the 25 percentile and the 75 percentile and the lowest value and the highest value. So here you can just see that lots of different people had lots of different stereoacuity values. This was an outlier. This is one test where this particular person had a really bad test and didn't do as well as they normally do. It's like 3 standard deviations away from the mean, something. Now, this is a good time to talk about the composite stereo depth score and how it is related to stereoacuity, and why we think, why Christy and I think it's so great and believe that it is the future. It goes from 0 to 30, or actually a little bit higher. And the range from 0 to 10, this is the range of values in this score where stereoacuity is not measurable. And so that's when you use percent correct at 3600. And we just translate percent correct to a number from 0 to 10. 0 is chance performance. That means you're just guessing. You had no idea. So in fact, you're going to be 25% correct because there's 4 targets, but that's what 0 is. no evidence for stereo ability at all. There's a score of 0. And then the percent correct is in the range from 29 up to about 80%, which is, once you're above 80%, you're in the staircase range. Once you're getting 80% correct, then that means you're getting you're going up and down within the staircase procedure. So these numbers are the rest of the percent correct range, 0 through 10, percent correct at 3,600 arc seconds. The range from 11 to 30 is then used to capture stereoacuity, and it goes as stereoacuity goes up, CSD goes down, and vice versa. So 0 is no stereo, 5 is poor stereo, 10 is still poor stereo, not as poor. 15, you have a measurable stereoacuity, and all the way up to 30. So greater than 30 is better than 20 arc seconds. And you might wonder, why bother with it? 2 reasons, or 3 reasons. The logarithmic scale is better for tracking progress, just like you would use logmar or lines on a chart to track acuity. You wouldn't like literally use the arc minutes subtended by octotypes. You would use a logarithmic measure like the lines, number of lines of improvement, or logmar. Same with stereo. Stereoacuity can't capture seeing in stereo some of the time, and so many patients, they'll start out by seeing stereo some of the time. Christy and I saw this in her dissertation work at SUNY all the time. We'd have patients who, they didn't have a measurable stereoacuity, but you give them the easiest stimulus in your test, and they're seeing it better than chance. They might be seeing it 50% of the time, 70% of the time. They're actually seeing it, but it just that it comes and goes. And we can capture that with this measure. Very important if you're working with somebody who's getting stereo for the first time. And then the other real benefit is we've now got a single smooth scale that goes all the way from 0 of no stereo to poor stereo to very good stereo. And as somebody, this is really valuable if you're trying to train somebody's stereoacuity system, stereo system, because you can use the same scale over time. You can average different people together if you're doing a study. You can watch smoothly. A person might be hovering right around 10, and they'll go, they'll have measurable stereoacuity one day and then not the next, and then get it again and then lose it again, and you're working them down into where you can measure it, and you can track that because it's a single scale. So now that we know what the CSD score is, let's look at it for these people. And here are the same 11 subjects, just plotted with the composite stereo depth score on the y-axis. And you may notice a relationship between these 2 charts, right? They are literally just, one of them is just upside down from the other. And that's because this one is just plotting the logarithm of stereoacuity, is all that it's doing, just on a different scale. Now the other thing that we kind of like about this method of measuring it is higher numbers are better performance. And as clinicians and vision scientists, we get very used to the idea that a low number is good in a stereoacuity test. But it's an extra cognitive step, and some people just naturally think of higher numbers as being more sensitive or better performance, and that's another reason for inverting the scale. We didn't have among these 11 who took this test, we didn't have any with really poor stereo, like Christy did in her dissertation work. Those were amblyopes. So in summary, virtual reality allows good measurement of stereoacuity despite the low spatial resolution of VR headsets. And that's that was the thing that we didn't know that we would be able to do. And it turns out we can, and it's really exciting. We've used a new specification, which is public. We're not hiding it the way, it's kind of hard to tell how some tests work. Not so much in vision therapy, but if you're familiar with doing Humphrey tests, it's hard to know exactly how the test works. You know enough about it to interpret the data, but not really exactly how it decides which intensity to show you where and when and stuff like that. Tests up to 3,600 arc seconds. It allows characterization of poor stereo patients by percent seen at 3,600. And that's what I want to tell you about. And let me see if I can now stop sharing.
All right. Yeah.
I should have a screen somewhere that will let me. There we go.
Okay, perfect. Thank you, Dr. Backus, for your knowledge and information on the new test. And anyone have any questions they would like to add in the chat? Unmute your microphone if you'd like to ask a question. We have a little bit of time here to get those answered for you.
Yeah, and I certainly don't object to having an efficient session today, so don't feel compelled to come up with questions if you don't have any. You can always ask me questions by email. So do that.
Wonderful.
I do see a question there.
Yeah, good. Do you see it, Ben, or I can ask it too? I'll ask it out loud. And are there any downsides, such as how the headset is centered for the person, whether it is level, etc.?
That's a really interesting question. If the headset is badly decentered, or if the patient's interpupillary distance is a lot smaller than the headset, then you will have optical distortions that will reduce the ability to measure stereoacuity. But it's surprisingly robust to small errors. If you just put the headset onto a patient, it does a remarkably good job. And what's interesting is in our initial testing, what we saw was you'd move the headset up a little bit on the head or down or left or right, and it would literally change which spot appeared closest, right? The optical distortions were enough, because your stereo is so sensitive, that when you got down to those very small disparities, you could actually cause a reversal of depth. And once we put in that grid behind the targets, it solves the problem, because even though stereoscopically this target might look like it's closer when the computer tried to render this one closer, because they're both against this common reference grid, you don't see it. And your brain pulls out the relative depth from the grid so efficiently that that's really what you see and what you base the answer on. So I guess the answer to your question is yes. There are some folks who if you're doing remote therapy and you know the person is just not capable of adjusting the headset on their head, or they're really not going to do that, then you might not trust the data. But it comes with a built-in. It really comes with a built-in method of knowing whether it's a problem, which is you can give the test twice, and if you get similar numbers, then you know that the display isn't causing a serious problem, especially if you have them take the headset off, put the headset back on. You could do that. We don't think that's generally necessary. I realized I was worried about time, and so I took out the slide that compares our results that I promised you, comparing it to other clinical measures. The real benefit of taking 100 seconds to do the test is that your measurements go up and down by a few arc seconds between tests. They're not going up and down by a factor of 2, right? So, you do word circles and the person is at level 4, and then they're level 6, and they're level 5, and then they're 4 again, and they're 6. Those are massive changes in the amount of disparity that people see. And we're used to thinking of that as, oh, the person's vision is variable. No, it's not that the person's vision is variable. That is not correct. It's that the test is imprecise. And what the person has is a % chance of seeing that is quite stable. But of course, if their % chance of seeing it at level 6 is 40, and their % chance of seeing at level 8 is 90, sometimes they're going to be at level 6, sometimes they're going to be level 9 or level 8, and they'll bounce around between those. So it's kind of a paradigm shift to say, yeah, the person's answers are probabilistic, but it's not that the patient is so variable, right? We can just collect, if we collect data for 100 seconds, we'll average that out and we'll get a smooth measurement, and they're only going to vary by 5 arc seconds from one test to the next.
All right, thank you. Any other additional questions or comments that anyone would like to add in the session here?
All right. Well, thanks so much. And yeah, if you do have other follow-up questions, let us know. We're testing it out now and hope to release it before too long. And we'll hope to get your feedback on it as well.
Wonderful. Let me type in, I'll type in clinical.
Anything else, Monica?
No, I think we're good here. I'm just going to type in a general, if there are additional emails or questions, we can send it to maybe the clinical team and then forward those to Dr. Backus here, or if you wanted to add yours into the chat, we could do that too. So we appreciate your time.
Okay. All right. Thanks a lot.
Thank you.
Have a good week.
Yep.
Bye-bye.